Hello and welcome back to Start Learning Wheels. And as always, I want to thank all the nice people that support this channel on Steady or PayPal. In today's part 4, I will show you how we can actually construct the real numbers. This means that the starting point is the field of the rational numbers, and then we form a new field where every Cauchy sequence is actually convergent. Now, because you have seen all the other number constructions, you might already guess that also here equivalence relations will be helpful. Our idea in this case should be that each point on the number line can be represented by a Cauchy sequence. For example, for the point 1/3, we can choose the sequence that has the members 1/3, 1/3 and so on. So it's simply a constant sequence, therefore in particular a Cauchy sequence and also a convergent sequence. However, the important part is that the limit is our point 1/3. Therefore, this infinite sequence of numbers represents one point on the number line. But now you should see that this representation can be in no way unique because we can just write down another sequence with the same limit. For example, we can just use decimals and start with 0.3. Of course, you already know this is just another notation for the fraction 3/10. And then the next member in the sequence should be 0.33. With this, we just continue appending 3's. Okay, with this we have a well-defined sequence where you can also easily check that it is also a Cauchy sequence. And because we get arbitrarily close to 1/3 eventually, we also know we have a convergent sequence with limit 1/3. So we can conclude when we form our equivalence classes soon, these two sequences here should land in one single box, simply because they have the same limit. However, you already know we cannot just look at the limits because there are Cauchy sequences in Q without limits. Indeed, for this we will find a simple solution. Okay, the first step is to define the set of all the Cauchy sequences we consider. So here xn stands for a sequence, which means an infinite list with the properties that for all natural numbers n, xn is a rational number, and that the sequence xn is indeed a Cauchy sequence. And this nice set that contains all the Cauchy sequences is denoted by C. Now, for two elements from the set, let's call them an and bn. So for two Cauchy sequences, we define an equivalence relation. Okay, at this point, we want that these two sequences here are equivalent, but we don't want to use the explicit limit. Therefore, the question is here, how can we do that in a simple way? For this, let's imagine that we see all the sequence members here on the number line. In the case that the two Cauchy sequences represent the same point, they accumulate around this number. So the sequence members get closer and closer to this point. Therefore, the difference between two members from the two sequences gets smaller and smaller. Hence, this difference is the new sequence we should consider. And now we already discussed that it should be a convergent sequence with limit 0. In other words, for any point on the number line, we just shift the problem to 0. Okay, now we have everything we need because we can show that this defines indeed an equivalence relation. This means that we can show the three properties: it's reflexive, symmetric and transitive. Now, as always, when we have such a nice equivalence relation, we can go over to the boxes where we put in the equivalent Cauchy sequences. And we call these boxes equivalence classes. By definition, the equivalence class of xn is just a set of all Cauchy sequences that are equivalent to xn. And therefore, this equivalence class now uniquely represents one point on the number line. To put it in other words, we now can actually define the real numbers. The set R is just given by the set of all equivalence classes. So the set of these boxes defines the complete number line. Now, the only things that are still missing are the two operations, addition and multiplication, and the ordering. Therefore, for the first part, let's define how we can add two equivalence classes here. Indeed, that's not hard at all. We can just use the addition we have for the rational numbers for all the members of the two sequences. Of course, as always, then we need to check that this definition does not depend on the chosen representation of the two equivalence classes. In this case, you just have to calculate a little bit with the sequences, and then we get out, yes, it's well defined. And afterwards, you will believe me that everything works the same when we define the multiplication. We just use again the well-known multiplication for rational numbers. Okay, now looking back at the axioms we want to fulfill, you see that the last thing we need to define is an ordering. So we want to define in which cases one equivalence class is greater than another one. Of course, here we need to use the ordering we have for the rational numbers again. However, claiming this for all sequence members is much too restrictive for us. To see this, please keep the number line in mind. For example, our bn's here could accumulate around 1/3. And maybe the sequence with an has 0 as the limit. But of course, we have infinitely many sequence members here. Therefore, for example, a4 could lie over here. But still, the limit would be 0. Hence, this inequality here should be satisfied only eventually. In other words, we can just ignore finitely many members. Therefore, we would write there exists a capital N, such that for all indices greater than capital N, we have an is less than bn. Okay, this now looks better, but it is still not correct. In order to see this, just imagine one point on a number line where the sequence bn comes from above and the sequence an comes from below. So they should describe the same point, but this one is still fulfilled. Therefore, maybe it's better to think in distances, so let's bring this one to the other side. Then it simply reads that bn minus an is greater than 0. Therefore, this means that the distance here could be arbitrarily small. And when you look back at the first example here, that's not what we want. So there should be an actual minimal distance between the 2 points. And maybe we just call this distance simply delta. So we simply have to add there exists a distance delta greater than 0. Of course, the distance delta could be very small. The point is it holds then for all n. Okay, there we have it. These are all the operations we need for the real numbers. Now in the last step, one can just calculate that all the properties we want, the axioms, are actually satisfied. For example, we can define the 0 element and the 1 element and show that we have a field again. However, the important part we have now by construction is the completeness axiom. Every Cauchy sequence is now actually convergent. With this, we can close this video, and I hope that you now know a lot about real numbers. And in the next videos, we will talk about the complex numbers. Therefore, I hope I see you there and have a nice day. Bye!